I want to thank everyone for joining us today. Um, our webinar today is Research Radar Driver Behavior, and it's hosted by the Minnesota Department of Transportation and the Minnesota Local Road Research Board. My name is Julie Swiler. We're excited to have our presenters Vic Lund, Nicole Morris, and Peter Savolainen joining us today. Today's webinar is the sixth in our new Research Radar series sponsored by MnDOT and the MnDOT Office of Research and Innovation and the Local Road Research Board. Each month, we highlight research projects focused on a common theme. MnDOT's Office of Research and Innovation manages more than 185 research projects in progress, ranging from local initiatives to pool fund projects with other states, comprising both basic and applied research. We're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your research needs, recommend the best research methodology for your project, access local and national funding sources, and manage your project from start to finish. The Local Road Research Board is a city and county-run organization that sponsors research and educational initiatives that address local transportation needs. You can stay up to date with our research by following us online and subscribing to our newsletters. We will send you a website and subscription links in a follow-up email after this webinar. We recently announced the funding of 27 new academic research projects selected from a competitive pool of 82 proposals. To see the full list of new projects, scan the QR code on the screen. If you have subject matter expertise in any of these projects and are interested in serving on the technical advisory panel, we invite you to reach out to our office. Before we get started, I will read you the Tennyson warning. This session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, simply turn off your camera. I'd now like to introduce our presenters. Vic Lund has more than 17 years of experience as a traffic engineer for St. Louis County, Minnesota. His experience includes rural and urban traffic safety, intersection design, intelligent transportation systems, and transportation research. Vic frequently serves as a technical liaison for Minnesota Local Road Research Board projects. Nicole Morris is a research associate professor and director of the Human Factors Safety Lab in the Department of Mechanical Engineering at the University of Minnesota. Her research focuses on human systems interactions with an emphasis on roadway safety for high-risk road users. Peter Savolainen is an MSU Research Foundation professor and chair of the Department of Civil and Environmental Engineering at Michigan State University. His research examines the fundamental nature of road user behavior, particularly how traffic and safety operations are influenced by behavior in consideration of roadway and traffic characteristics. Now, to get started, I'm going to turn things over to Vic Lund.
All right, well, thank you for that, Julie. And Nicole is going to bring up our presentation here momentarily. All right, there we go. Well, thank you and good morning, everyone. Thank you for joining us today and appreciate your interest in these local road research board projects. I am the technical liaison on this particular project with Nicole. She's acting as the principal investigator. Looking at driver behavior at rural intersections, specifically thinking about J-turns, and we'll go right into the next slide here, Nicole. All right, when you look at all serious crashes in the state of Minnesota, intersections continuously and consistently are a major or a significant generator for all those serious crashes, particularly along the multi-lane divided highways like rural expressways. And in fact, MnDOT is having policy discussions ongoing as we speak about different ways of treating those intersections in terms of restricting access, looking at right-in, right-outs, looking at J-turns, looking at closures, those sorts of things, because they continuously generate those serious crashes historically and unfortunately going into the future. But you think about why those crashes are happening, and we have to think about from the driver's perspective on the side street. In most cases, we're asking that driver on the side street to have several layers of decision making at one period of time. And that tends towards increasing those risks for crashes because, that driver has to think, are there available gaps? And okay, if there is an available gap, I see a vehicle perhaps coming down the major highway from some distance. What's the estimated speed of that vehicle? Because I have to understand how much time I have to make my maneuver. Well, if it's at a rural expressway, what if there's an oncoming vehicle and coming into that median opening, and I have to share that median opening with that oncoming driver? How am I going to route myself around that? And then on top of that, there's navigation. Well, where am I going? And if I have a complex intersection, I have to be thinking about how I'm navigating through the intersection to get to where I'm going, but I also have all the other vehicles that I'm interfacing with. And so, unfortunately, when we put those multiple layers of decision making on top of a driver, it increases that risk of that driver making a poor decision. And I'm not going to get into the whole conflict point aspect of that, but that's one of the things that we look at is how do we reduce conflict points? Because in a sense, that's a surrogate for a high level of decision making. So the complexity of these intersections certainly can contribute towards those serious crashes, but specifically the crash types that we're most concerned with at these rural expressway intersections are those T-bone or those right angle type crashes. Almost most of the time, nearly all the time, all the serious crashes that you pick any random rural expressway intersection with a county road or a township road or even a state highway, and the serious crashes are going to tend to be the ones that are just right angle crashes. Their side swipes, the rear ends, perhaps even the left turns aren't necessarily seeing those types of severity outcomes as a T-bone crash, which leads us to the next slide, which is the J-turn concept. And this J-turn concept has been around for some time in Minnesota. I believe the first one was constructed in about 2010, approximately. As of last summer, this is a screenshot, by the way, of all the J-turns constructed to date on the MnDOT website. But as of last summer, in Minnesota, we've constructed our 100th J-turn. And of course, many are coming. Here in St. Louis County, I'm leading 2 projects to construct 2 J-turns this summer. They work. And if we go into the next slide in terms of why they work, they're proven effective. They've gone through academic study. Every time we put one in, we see these academic studies come to fruition in the sense of that reduction. We're seeing about that 80%, perhaps even higher in some cases, reduction in serious crashes every time we install a J-turn. And oh, by the way, the history here, when we look at the experience, the safety performance, these J-turns were installed at some of the worst intersections, and we're seeing those levels of reductions. As a traffic engineer, I get excited when I see 30, 40, 50% reduction in serious crashes. When you're getting that 80+%, it's a special treatment. That's why you're seeing so many of them deployed so far and wide here in the state. But we have different design concepts. Some J-turns have mainline lefts that are accommodated. Some we just have median openings. But the signing density as a result tends to be higher at J-turns because of all the indirect maneuvers. And so of interest to us as traffic engineers, practitioners, and with our researchers like Nicole, is there an opportunity to reduce that sign clutter? In other words, what level of information does a driver need to successfully navigate through a J-turn? And are there opportunities to reduce some sign clutter out there? And to make navigation perhaps even more intuitive, right? Maybe there's condensing signs into maybe different messages into one sign. Maybe some signs we don't even need altogether. Good question. But with that, I'm going to turn it over to Nicole, and she's going to get into the actual research here of looking at driver behavior, navigating through the J-turns. So Nicole, take it away.
Thanks, Vic. So we've had a great opportunity to do a series of studies examining J-turns from a multiple kind of aspects. The first is looking at community acceptance So to Vic's point of this really being such a life-saving intervention to high-risk intersections, it's important that the communities are accepting of these intersections when they are proposed. And if there's strong community pushback, that can result in delays, increased costs. And to that, we find in a study I'm going to discuss in a few moments that initial errors that drivers experience on these intersections, some of these initial confusions, can really kind of poison the well, so to speak, for their acceptance of these intersections, leading to sort of word of mouth discussion across communities about these being good or bad. So it's really important that people are accepting and they have good experiences, particularly good first experiences. So I'm going to talk a little bit about the types of errors that we've been observing at J-turn intersections, and then some of the studies that we've been doing to try to see in what ways can we mitigate these errors through signage and design. So just really quickly, I want to touch on the work that we've done, and this was also MnDOT and local road research funded research into the types of educational messaging. So the use of educational materials like brochures, flyers, presentations, but also customized messages and strategies. And we find that more than anything, there's really no bad way to educate. I think the more education that we can do early and often before people form strong opinions about J-turns is really important. So we tend to find universally people's opinions tend to go up after they experience some education, particularly about the benefits, the costs of these versus other more expensive interventions to intersections. I'm going to play one short testimonial here. And this is one of our favorites, and I think really hits on a lot of questions, and tends to be a really trusted voice and is well tested in our research. But it's occurring to me, can you hear that?
No.
Okay.
We can't.
I'm going to stop.
Can you share?
Yeah, thank you. I'm going to stop sharing. There we go. Thank you. We tested this out and then I didn't do it as planned. Okay, here we go.
James Irwin with the Lumacraft Boat Company. I'm the president and general manager here. I've been here since 1995, and Lumacraft's been in St. Peter since the early 70s. Well, I think the first concerns we had was our semi trucks that deliver our product from here. So our misperception is that U-turn going to be difficult to navigate? Is that U-turn going to be hard for the truck drivers to work with? And the biggest answer is when we talked to some of our truck drivers that have experienced them already, they all were in favor of them. They see the benefit of how it reduces the conflict. They think it's actually easier to navigate in the end. And so I think, trust the people that drive daily. Trust the truck drivers. They're the ones that have been through this, thousands of times. They know what they're doing. We did do kind of an educational piece to hand to some of our vendors that deliver here, just so their drivers would know that this was coming and what to deal with, so they knew how to still get here, especially during the road construction, but even afterwards. And for the most part, we got good feedback on that they appreciated it. But again, most of the truck drivers had experience with it, and their U-turns aren't that bad. That was probably our biggest misperception, is just thinking the U-turn would be difficult. Okay. I like them. I've actually got experience with both the one here in St. Peter for work, and then actually there's one just south of my house, the one on Highway 14, and I think it's with 27 there, just outside of Eagle Lake. Once you get the hang of them, they're easy, and you can see how they reduce, the potential for accidents, or if you're going to have one, it's going to be a lot less.
So it's a great testimonial. It's a good example of tapping into your local audiences where you have had a success story of a J-turn, someone that's trusted. This isn't a authority figure or somebody that works for the state. It's a business owner. And so I think this type of testimonial can be really powerful. You can do these either through your communications, in your town meetings, or even having an in-person representative there to give a testimonial. We've also seen good success with the use of state patrol troopers who can speak to some of the horrors that they have seen at these risky intersections, and then the abatement of those after. So I really encourage you to look into testimonials, and certainly feel free to reach out to me. We have these posted onto YouTube. And so we're more than happy to share them. I think they still can even have value outside of Minnesota if we have any members of the audience outside of Minnesota. So we do find that the novelty of the intersection. Of course, this is going to get easier here in Minnesota and other states the more J-turns that you install. And so the novelty will start to diminish, but still you're going to be capturing drivers who are going to experience these for the first time and feel like they're really counterintuitive. And, these are just kind of crazy things that these engineers are coming up with. So certainly can cause some initial errors and some dissatisfaction. We have found that, the first drive that they tend to have more major and moderate errors. So major errors like missing the U-turn altogether. That could be very frustrating if you have to drive another mile down to turn around. More minor errors tend to occur later on. So after they have more exposures. But we do find that if they have a more major error on that first exposure, their acceptance and their willingness to drive on the U-turns or want them in a community tends to really tank. So we want that first experience. It's all good and well to say, oh, people learn these over time, but it's really important that they get it right from day one. One, we don't want that first experience to be cataclysmic where they have a collision, but also we just don't want them to, drive away with a bad experience. So we have a really immersive driving simulator in my laboratory. And so we've presented drivers. This is a real intersection near Heron Lake in Minnesota that we modeled. It is a compact J-turn. So you can see from the stop as they're coming down from the top of the image, they're supposed to drive immediately into that deceleration lane. But we tend to see kind of a range of errors, less frequent, but we did still observe in the simulator people driving through that middle, so a wrong way through that permissive left turn, which obviously could be very dangerous maneuver. The middle one here is just someone full on missing the U-turn, so they make the right turn and they don't change lanes, they don't get into the deceleration lane, and they drive on past. Versus a more common type of error that could result in sort of a more minor crash, like a side swipe crash, which is a late turn into that deceleration lane. That's one of the most common errors that we saw. In this study was people having a hard time knowing that they needed to drive straight into that deceleration lane, resulting in a lot of kind of very quick last minute maneuvers to get over once they realize like, oh, that's where I'm supposed to go. I need to get into that U-turn lane. So to show a little bit of validation of, there's always sort of question, is the behavior that we see in the driving simulator, does that match what happens in the real world? So this is a video that we took up in District 1. So this is a new J-turn intersection near Homestead Road and Highway 61. And so this vehicle was at the stop sign, should have turned, I'm going to play it again, should have turned and gone down to this U-turn and come around, but did not. So went into that left turn. So what's interesting about this turn or this intersection is it does have a permissive left only from one direction. And so in cases where you're seeing a lot of this behavior of wrong ways driving through the middle, it could be intentional. They know they're not supposed to do it, but they do it anyway because they don't want to take the U-turn. Or sometimes drivers are just genuinely confused and not sure how to get across any other way. So they feel like it's wrong, but they do it anyway. Eliminating all permissive lefts and forcing all drivers to use the U-turn could be a solution. So the question is, how much signage do we need? And so this was from that original study. And so we kind of had 3 different layers of signage, either just the black signage, layering in the black and the blue, or all 3 colors. And so the question was, are drivers really supported through more signage? Are we getting the right bang for our buck? Is it reducing errors? And we found that the errors that we saw in them navigating the intersection wasn't really predicted very much by the signs. The most predictive piece to the errors was just their experience. Over time, they tended to get better. But interestingly, even though they tended to kind of in some ways report being overwhelmed by the amount of signs and that max signage condition, they still felt like they needed enhanced signage or on-road markings to guide their travel. So it just sort of gets to this idea that you have to make sure that the signage is appropriate and is really giving them the information they need. They tend to get overwhelmed and the signage that's present may not be helpful. So in our current study, we're looking at, how can we change some of the signage to better guide their navigation through the intersection, particularly knowing the types of errors that they tend to make? How can we try to mitigate those? So we're looking at an extended U-turn and a compact U-turn. So the extended, you would be making a right turn and making lane changes to get over to that U-turn, which is further down the roadway, versus a compact where you're going to drive right into the deceleration lane. And we're looking at kind of some control signage the way that it typically is done versus some experimental signage. So one thing that we are looking at is the fishhook signage. So having that more visible to really sign out that they're approaching a U-turn and give them that bird's eye view of what they're about to approach. And also some on-road marking. This is a implementation that we're testing just for the compact signage, not the the compact U-turn, not the extended, to guide their movements straight into that deceleration lane. Because if they don't enter it right away, then they have more opportunities for error and the side swipe crashes. So we need to get them right into that deceleration lane. So that's one of the things that we are testing. This is what it looks like from the driver's seat in my driving simulation. We do have these signs slightly oversized just because we don't have quite the same resolution as you would in the real world. And we're also looking at the fishhook on the U-turn signage versus the straight arrows. This is new guidance from MUTCD that we think there could be some opportunities for confusion, particularly if you have a county lane that coincides with that U-turn, may confuse drivers about where they need to go. So our preliminary findings so far, we're aiming for 60 participants, so we're about a third of the way through. This is our sample. A lot of drivers from urban and suburban areas, so not as familiar with these J-turns as you would in rural areas of the state. So we have a lot of data that we pull out of the driving simulator, but for instances like this, we like to do what we call live air coding, so we can be looking at our results in real time. So we have lots of cameras on the participants and on the simulation. And what we're finding is that they certainly are still making navigational errors, so not following the instructions of what roadways are supposed to get into in which direction. And we are seeing that late turn into the deceleration lane is occurring, again, particularly more with the compact U-turn. So that's a really common error, again, likely for them to miss the intersection. And we are finding that compact U-turn intersection is more error prone than the extended U-turn intersection. And as with the other study, we are seeing, thankfully, that the errors tend to diminish pretty quickly. But we don't have enough data at this point to determine whether or not our signage is having any significant impact on the errors that we're seeing so far. So moving forward, we'll continue to collect the rest of our data to get to our target 60 participants. And we also have then a corresponding intersection, the video that I've shown you previously of the driver cutting through at Homestead Road. So we have another round of data collection that we're going to be doing to look at changes over time. We have video from before the intersection was installed, just after the intersection is installed, and now about 8 months later. So our goal is to really provide some design guidance about potential signage changes and marking improvements. And this is my email. So again, if anyone is interested in access to our testimonial videos or any other educational materials, happy to share that. And I'll hand it over to Peter.
All right. Thanks a lot, Nicole. And thanks to everyone for being here today. I'm going to give a brief overview of some work we completed about a year ago titled Complete Street Speed Impacts. And so my thanks to Dwayne Hill and to the other TAP members, as well as MnDOT and LRRB for sponsoring that work. And so I'll basically give a big picture overview of the study. I'll talk about how we selected sites, what we did over the course of field data collection, and then I'll run through a bunch of our analyses and some of the insights we gained as a part of that study, culminating in our conclusions and recommendations, and then touch about some limitations and some ongoing work that's occurred subsequent to this and other work that's planned to start this summer. And then at the very end, happy to handle questions and answers, but if you have any in the meantime, please feel free to type those into the chat. And so I'm sure many of you in the audience are familiar with how we historically have established speed limits. There's largely been a reliance on the 85th percentile speed, and with Vision Zero and safe systems approaches to traffic safety, we've seen kind of a shift away from that. NACTO, of course, had advocated against its use back in 2017, and similarly, the National Transportation Safety Board had recommended changes to the MUTCD, and we have subsequently seen those come into effect as part of a broader effort to help to make roads safer for multimodal users, especially pedestrians and bicyclists, as opposed to the more vehicle-centric approach we've used historically. And so to that end, Minnesota, as you're also likely aware, has a statute that advocates for a complete streets approach to roadway design that considers safety and accessibility of all users of all backgrounds and characteristics. And so an important aspect of that is trying to select appropriate design speeds or target speeds. And as a part of those efforts, we often use complete street policies to try to modify some of the cross-sectional environments. So varying lane and shoulder widths, introducing bike lanes and various other features that help to make it safer and more accessible for that broad range of users that we're concerned with. Now, unfortunately, historically, there's been surprisingly limited research as to what the impacts of some of these different features and treatments are on actual travel speeds. And so that was ultimately the big picture goal of this project. And so what we were trying to do ultimately was answer the three questions you see here in front of you. So first of all, when we go predominantly from high-speed rural highways into, say, rural communities, for example, how do drivers reduce their speeds as they see speed limit reductions introduced? And then in turn, beyond the speed limit, what other elements related to the roadway environment help to reduce those limits? And then how do those effects carry over downstream of where those features are introduced? And then also on the upstream side, when and where do they start those speed reductions? And so ultimately trying to look at those factors and combinations so that we could then develop guidance that would help you all as designers to make more informed decisions as to how you can help better control speeds through these different types of roadway environments and communities. And so at the onset of this study, we had worked with the technical advisory panel, and you'll see here, we selected 19 corridors from various areas across the state. And along those corridors, we basically had 39 different segments where we set up speed observations using high fidelity LiDAR data collection devices. And so I've got to acknowledge the efforts of my students and staff who were out there for many hours tracking vehicles with LiDAR. And so as we look at the characteristics of these sites, data were collected during off-peak weekday periods. We wanted to be able to capture free-flowing traffic. So we're looking at minimum headways of 3 seconds. And you'll see on the right here just kind of a table summarizing the ranges of speeds we saw in those corridors. So oftentimes those rural highways would have speeds of 55 or 60 miles per hour. And those would be reduced to 45, 40 down to minimum speeds of either 25 or 30 miles per hour. Typically, these were in speed transition areas, so on the approach to small rural towns. And in addition to that, we tried to select these sites so that we had a diversity of geometric features, so different median treatments. So we had some cases where we had raised medians, two-way left turn lanes. We sought to understand if there were impacts of on-street parking, shoulders versus curb and gutter. We had some bike lane sites. We had some sites with curb outs, etc. And so schematically what we did then is we basically had data collectors out in the field using LiDAR guns, and they would basically be in sequence of either 2 or 3 observers as you see here. And what we would try to do ultimately, the first data collector would track a vehicle as they transition from that higher speed rural environment entering the small town. And then as those speed limits were reduced, we would hand off to the next data collector in sequence. And in some instances, we had multiple speed reductions. And so we'd add additional data collectors in those instances. And beyond just capturing when we saw speed limit reductions. We also had concerns with capturing other aspects of changes in that cross-sectional environment as well. And so as I transition to the next slide here, this will just basically show you a sample speed profile from one of the sites on Minnesota 37 and Gilbert, where the first data collector was collecting near the 60 mile per hour upstream limit to a reduction of around 40 miles per hour. We then handed things over to the second data collector as we approached the lower 30 mile per hour limit. And then we had some other features that were introduced there, for example, a bike lane that came in subsequently. And so what we were able to do, rather than just observing vehicles at given points as we would in a spot speed study, the LiDAR data allowed us to have much richer information to understand the nature of those changes and how they varied over time and over space. And so as we look at the next slide here, this is just an example. So the orange dots you see here are basically individual vehicle speed profiles along that same corridor I showed on the preceding slide. The blue is basically an average of those, and we basically use some data smoothing techniques, as you see when we move to the right over here and these lines become a bit smoother. And then we've also marked off where speed limits change and where other features of interest are introduced. And so subsequent to this, we had conducted a statistical analysis to try to understand what are the impacts of those speed limit reductions and what are the impacts of those other features that are sometimes introduced concurrently or upstream or downstream to where those speed limit changes went into effect ultimately. And so now I'll basically briefly walk you through some of the study results here. So I'll start generally with just a table of descriptive statistics here. So I won't read through everything in great detail here, but we had good coverage of speed limits from 25 up to 60 miles per hour. Roughly 90% of the sample was passenger cars and 10% heavy vehicles. And then we had a range of different types of geometric features, as I mentioned, different median treatments. We had some intersections, stop control, either on the minor leg in the 3 or 4 leg case. We had instances where we had crosswalks. We had some bike lanes, etc. And then we also had some variability as well in terms of lane and shoulder widths. And then some of the sites had medians, some of them didn't. And we also looked at the widths of those medians to the extent we could. This is the only equation you'll see here, and I just bring this up basically to tell you what we did from an analysis perspective, and again, an advantage of the LiDAR, rather than observing vehicles at individual points, we tracked each individual vehicle here. And so we were able to account for the fact that some drivers inherently tend to go faster or slower than other drivers, all other things considered. And so that basically allowed us to get more precise estimates as to what the impacts of some of these different features are. And so if anyone has questions on the stat methods portion, I'd be happy to handle those subsequently here, but just wanted to give you kind of an overview of how we went through and conducted the analysis to try to determine ultimately what these parameters are that tell us what the impacts in essence are of these different features. And so on the left here, you'll basically see some parameter estimates from those statistical models. And so first of all, the average speed upstream before we get into the speed reduction zones was around 64.5 miles per hour. And you'll see here what's happening. These are basically telling us as we're approaching a speed limit reduction from upstream, this tells us how those vehicles are starting to reduce their speeds. And so you'll see generally we saw this nice smooth profile here. Vehicles would start to reduce speeds roughly 800 feet upstream of that first reduced speed limit sign there. And that was fairly consistent site to site. And you'll notice fairly smooth reductions here that became more rapid as we got nearer to the speed limit reduction sign itself. And as I click ahead to the next slide here, we also track those vehicles beyond that speed limit reduction. And so you see here those vehicles continued to reduce their speeds, and then it would start to plateau roughly 400 feet downstream. And so from that point forward, we tended to see relatively stable speeds. A quick note here, this profile on the front end as we approach the sign from upstream was fairly consistent. Some of the variability you see here is due to the fact that sometimes we'd have a second speed limit reduction, and so there's a little bit more noise there. But we were able to tease out some of the effects of not only the speed limit signs here, but some of the other factors of interest. And I've got to credit Dwayne Hill for coining the term speed reduction factors, which I'll get to in a moment here. And so this next set of parameter estimates here basically tells us how much speeds are reduced by as we reduce that speed limit from 60 miles per hour to some lower downstream limit. And so interestingly, what you'll see at the very top here, even in the 60 mile per hour section, we'd see speeds were reduced by up to 8 miles per hour whenever we got within a half mile roughly of the town or of where that first speed limit reduction sign was introduced. Beyond that, we'd see subsequent reductions typically in the range of 3 to 5 miles per hour, which is consistent with a lot of the empirical research that you'll see there. And so this gives us a sense of what kind of differences we'd see based upon what those prevailing limits are. And then what we're ultimately interested in down here are what are the effects of those different geometric factors on speed selection. And so the strongest effect in our case, there were a few sites that had single lane roundabouts, and we basically saw those reduced speeds as vehicles were entering and exiting the roundabouts. They were maintained for roughly 500 feet upstream and downstream of the roundabout. We also saw significant reductions when we had a raised median. And so, again, in the more urbanized areas, these often provide pedestrian refuge islands, and they're another visual cue to drivers that they should look at reducing their speeds. We also saw smaller effects, but reductions when we saw depressed medians or two-way left turn lanes. So these are all basically compared to our baseline condition, which was an undivided two-way roadway. We saw areas that had on-street parking were about 1.7 miles per hour lower speeds on average. And I think one of the more interesting findings, the sites that had bike lanes were marginally higher in terms of average speeds, just 0.4 miles per hour here roughly. While concerning on the surface, I should note we didn't see any bicyclists occupying those lanes while we were conducting those studies. And so we're actually set to start some follow-on work this summer where we will be observing these same sites as well as some other sites when we actually have those bike lanes occupied by our staff or by people who are naturally bicycling in those communities. We did also see reductions in speeds when there were crosswalks, and this was irrespective of whether there was a pedestrian present there or not. So we're hopeful that's reflective of just some visual cues and better cognizance on the part of drivers who are approaching those communities. And then curb and gutter showed roughly 1 mile per hour lower speeds than if we just had shoulders in those areas. Stop control on the minor road, not much of an effect there. And so this kind of gives you a general sense of the nature of these effects. I think the next slide does perhaps a better job of illustrating some of these trends graphically. And so basically what we see here, the 0 point, it's kind of like a baseline condition. And so as you look at the top here, you'll see heavy vehicle speeds were on average nearly 2 miles per hour lower than passenger cars. And then for all of the geometric features we looked at, except for bike lanes, we did see speed reductions with, again, the strongest reduction there being the presence of a single lane roundabout. And then the next two sets here, this shows as we're approaching that speed limit sign from upstream. So this is far upstream. And as we get nearer and nearer to that sign, these speeds get lower and lower. And then those same trends continue as we get downstream of that sign. And that's what you see here graphically as well. And then what we are basically recommending for inclusion in MnDOT and local design guidance are these speed reduction factors. And so we have a general sense of, on average, if you introduce these features, this is what you could expect to see in terms of impacts on mean travel speeds. Now, in addition to mean speeds, there's other factors that are important as well. Of course, if we've got high variability in travel speeds, that's been shown conclusively to increase the risk for crashes. And so what we did, in addition to mean speeds, we looked at the variability in speeds, basically at 50-foot increments as vehicles were traversing these corridors. And we estimated some regression models. I've omitted those here, and I'm just going to show you some of the graphics here. But in this case, this is essentially comparing to the average standard deviation is what this zero line represents here. And so not only with those geometric features did we see reductions in mean speeds, but generally speaking, we tended to see reductions in the standard deviation or variance of speeds as well at those sites. We saw a bit more variability on the upstream approach, and this makes sense. There's some drivers who reduce their speeds sooner and more gradually. There's others who would tend to reduce their speeds more rapidly and nearer to where that actual speed limit occurs. And so that's why you see higher variability here. But once we get downstream and into that lower speed limit area, we see not only are speeds lower, they're also less variable. And so with that, we're hopeful that that would then translate to lower crash risks as well. In addition to variability in speeds, we also looked at an important aspect here in terms of compliance with the speed limits. And I think unsurprisingly to many of you, more than half the drivers across the widest range of limits tended to exceed that posted limit. We also looked at how many were 5 miles per hour over. And so we see a bit of variability there. Compliance tended to be best in the high speed immediately before the reductions went into place, and also in the lowest speed areas. So we saw poorer compliance in those intermediate speed ranges. And then as we look at some of the effects from the related statistical analysis graphically here, we do see here, so this is non-compliance. We like to see lower numbers here. So we see the same general trends. So the geometric features are reducing mean speeds, they're reducing speed variance, and they're also improving compliance with the posted limit there. And so I think the fact that we're seeing all three of those metrics repeatedly for each of the features of interest provides some additional confidence in what we would see with these results at other sites as well. And so wrapping up then, just in terms of some conclusions and recommendations, as I had alluded to in the preceding slide, we generally saw the best compliance immediately upstream of where those speed limit reductions occurred, and then also in those lowest speed environments. And so that suggests from a policy or practice standpoint, if we focus in that moderate speed area, so say 35 to 45 miles per hour, that's where we might see countermeasures have the most promise for effectiveness. That speed reduction, again, consistently starts roughly 800 feet upstream and continues those reductions 400 feet downstream, at which point they tend to plateau. Another question that arises from that is how far might that continue beyond 400 feet? And that's something we're continuing to look at. We looked at a few other factors as well. So median width, we didn't have a lot of variability here. So we actually have some follow-up work where we'll be working with a technical advisory panel to identify a few sites that have medians of varying width. Lane and shoulder width, we didn't see as much variability. So predominantly we saw 11-foot and 12-foot lanes. We're hopeful to get some work. I think once we get down to 10 feet, we'll see a bit more pronounced effect there. And similarly, the shoulder widths tended to be a bit wider in some of these rural communities as we were coming into those towns. We're also looking at potentially at if we see isolated islands rather than continuous medians, whether we see any differences there. But in this initial study, sample sizes really weren't large enough that we could show any conclusive effects. And so from the agency perspective, what you're probably most interested in here are those speed reduction factors I had alluded to. And so the hope here, we actually have some follow-up work that's going to start in the state of Washington in about a month. And we're doing some companion work here in Michigan as well. And so the hope is through all those studies collectively, we can integrate those results and really give you all good ammunition as designers in terms to better understand how we can help to keep those speeds in that target speed range that we're most interested in. Roundabouts, again, beyond the safety improvements, we see sustained effects there. speed reductions of up to 7 miles per hour. And we've seen this in other locales as well. So if you think about corridors that have roundabouts at some intervals of spacing there, that's a promising speed control measure. And then the median treatments, that physical barrier in the presence of the motorists and that refuge for pedestrians and bicyclists tends to have a sustained effect. We're going to investigate on-street parking a little bit further as a part of some of our follow-on work here as well. So there's questions about parallel versus angle parking. I mentioned the bicycle lanes. So we did see marginally higher speeds there, but important to note that there weren't any bicyclists present at that time really. And we're also planning to look a little more in depth at the differences between shoulders and curb and gutters. And so as we look at this from a big picture standpoint, as we mentioned, most of the features that were of interest to the TAP did show at least some degree of efficacy. And so now it's a matter of trying to determine which treatments and combinations of treatments work best in different settings, and trying to focus again on lowering the mean speeds, the variability, and improving compliance as well. And so wrapping up here just with some limitations and future research. So one of the big ones there, we did see lower speeds with crosswalks, but we didn't see a lot of ped activity, and then marginally higher speeds with bike lanes. We're going to investigate those further in a soon to launch project. And then there are a few other different types of features that we may potentially look at. Nighttime data collection is a little bit tricky. That's one we'll look at a companion project that's focused on speed limit reductions, where we'll use radar, basically black cat radar devices, since we can't really effectively, for the safety of our data collectors and from an efficiency standpoint, do that. But there's a few other things we aim to look at here as well. And then ultimately downstream, once we have all the speed data in hand, we can also start to look at what some of the safety impacts are here as we look at things like crash modification factors that could be tied back to those speed reduction factors. So my apologies, I think I went over about 2 minutes there, but hopefully we're good in terms of questions. And so again, thank you all very much for the time. And if you have any questions, I have perhaps the easiest email address, at least at MSU, and that's just pete@msu.edu. So thank you all very much.
Thank you. Thank you for both our presentations. We do have time for questions, so please put your questions in the chat. We've got some started already. If you want to raise your hand and ask the question directly, feel free to do that as well. And I'm going to start with a question from Elizabeth Hickson for Peter. Was the presence of vegetation close to the road considered as a factor for slowing speeds?
No, and that's a good question, and that's come up kind of separate to this. And so we actually have a companion project that my colleague Kakan Day is working on, because I think that's a good question. If we look at like tree canopies and other vegetation in the median, for example, I suspect that might have an effect, but that wasn't one of the focuses in this initial research.
Thanks. Our next question is from Brian Tang. Crosswalks equal marked crosswalks without any treatment?
Correct. So that was just the presence of a marked crosswalk in those instances. We have done companion work, and I know Nicole's group has as well, looking at how different crosswalk configurations affect yielding behavior, for example. But I think there's also potential there in terms of reducing speeds in addition to that yielding that we're all interested in.
Thanks. So I apologize ahead of time if I mispronounce your name. Kare Festvog is asking, do you think posting transition speed limits decreases variability?
Yeah, so I guess based on what we've seen up to this point, I wasn't sure what we would see going in, but as those limits were decreased, not only did the mean speeds reduce, but we generally saw significantly lower variability in those speeds as well. So I think that's promising, and I guess I should also clarify here, I don't know what we would see in higher speed environments. So we've got a lot of questions about, say, freeway speeds here in Michigan, where we've pushed our limits up to 75, but certainly in these lower speed areas that we're focusing on here, those transitions did seem to be effective from that perspective as well.
Thank you. From Leah Nisler, Is the Daimler law in Minnesota has to do with exceeding the speed by less than 10 miles per hour does not go on your record for over 50 miles per hour over roadways affect driver behavior? Have you heard time and time again that drivers go 5 to 9 miles per hour more than the posted speed, cause probability won't get pulled over? If I explained that properly.
Yeah. So I'm not certain. I could speculate here perhaps. I guess there's a rule of thumb here in Michigan that if you're up to 7 over, you're safe. Now, I won't testify in court that that's a true thing. So don't put me on the spot for that. But as an example, when we go to Ohio and there's a Michigan-Ohio rivalry, people say they're less comfortable going beyond 5 miles per hour for fear of getting a ticket. So trying to investigate that, I guess we'd need to know when that law went into effect, and then depending upon what we had in terms of historical data, maybe we'd see some things there. Now, we did look at impacts on compliance with the speed limit overall. We looked at 5 miles per hour, 10 miles per hour over. So we do have access to that data, but I guess I don't know when that law went into effect and what we might have historically. But my inclination is we probably would see impacts at some of those thresholds, whether it's 10 miles per hour or 5 miles per hour.
Thank you. Howie Preston is asking, consider looking at the grade of the roadway as a potential speed reduction factor. Where there is a sagged vertical curve in advance of the lower speed limit, gravity can help slow approaching vehicles.
Yeah, so that's a good question. Now, we didn't look at that, and there's various reasons for that. We didn't look at horizontal or vertical curvature explicitly here, and that's because we're using LiDAR to track the vehicles. And so there are cosine effects that kind of complicate things. We can look at alternative data collection measures, like we can just do point-based radar data collection, or we could use cameras there. And so that's something just we haven't looked at up to this point, but certainly something that would be a factor. And I see the follow-up, is this research published? Yes, the report is out, and we had a TRB paper that was just accepted, and I've got to check with my students as to whether we've approved the proofs on that or not, but that is out there for you all to see.
And I will just say that we will be sending you a recording of this webinar and all of the research, links to all of the research that's been talked about today after this webinar is over. I have a question for Nicole. I'm curious regarding J-turns, if driver's ed programs include J-turns in their education, and if you think that, if not, would that be something we'd look for in the future?
I think that's a great question. I unfortunately don't know the answer whether or not driver's ed includes J-turns. My best guess is probably no. It's incredibly difficult to add new content to driver's ed programs, and it's a really dispersed type of a setup. So you have a lot of kind of contractors, and there's a lot of research questions out there about consistency more generally across driver's ed programs. So perhaps Vic or someone else in the call could answer that question. But I do think that the more that we can do to educate people about some of these novel intersection designs, along with J-turns, I think, obviously my team works a lot with J-turns, but we really try to use this as just a good example of the types of work that we should be doing about education, and looking at navigational errors around other types of novel intersections, diverging diamonds, and also roundabouts. So we find a really strong relationship. You better bet if somebody doesn't like a roundabout, they don't like the J-turn. And so we find a lot of similarities across drivers' perception. And really a J-turn is really kind of like a squashed, elongated roundabout. So I think that there's a lot of work that we could do to help better educate people on alternative intersection designs, because they're just going to become more and more common and more integral as we're working on our Towards Zero Death initiatives.
Yeah, I'll just jump in real quick. I can say this from I guess an anecdotal standpoint, but I do have 2 older kids that one of them does have their license, one of them is in a permit phase. And I say this with some intrepidation as a traffic engineer, because they're going through that process right now. Indeed, I did ask my kids, are they talking about these types of intersection treatments, roundabouts, J-turns? The one instructor they had was actually talking about it, which I was really pleased to hear. But I have no idea in terms of the content and what is developed and that sort of thing. So I think it comes down to exactly what Nicole was saying. Education is extremely important, and there's probably a lot more conversations to be had of how do we get this information to our younger drivers.
Thank you. We had a comment in the chat that Peter did answer. I'll just read this for everyone. The comment from Timothy Thoreen was, the curb and gutter finding is interesting. I'm curious if you intended to looked at the combination of factors where a rural section with a ditch transitions into an urban section with curb gutter. It is often transitioned specifically that is cited as a traffic calming device. Do you want to speak to your response, Peter?
Sure. Yeah. So that's what the preliminary results suggest, and that is one of the factors we're intending to look at in greater detail as a part of the phase 2 work that it's scheduled to launch about a month from now. So thanks for that question.
We still have a couple of minutes. Do we have any other questions? We did get a request to get she had a link to the YouTube page you referred to, Nicole, and that's another thing that we can include in our in the information that we send out probably tomorrow. So,
yeah, absolutely. Yeah, I mean, it's a great question about the renewing driver's licenses, and more and more states are stretching out that process, making it a really kind of abbreviated renewal. And I think, of course, we always want to capture novice new drivers because they're so at risk. But you're a team driver for a short amount of time, and then you're a problem for the road for another 50 plus 70 years perhaps. And so it's really important that we try to find ways to capture all drivers through those renewal processes. I do see someone says J-turns are in that Minnesota driver's manual, so that's great. So hopefully we are capturing people, but I think it is just a lot of drivers on the road, and it will take some time to get everyone up to speed on what these are.
We had somebody request that the J-turn at Highway 23 and the Interstate 94 in St. Cloud be investigated, and it is, I'm looking for the answer here, apologize. And we got a response that there is a report available on this, which again, I think we could include that with our information that we send out to you. Brian Tang says the tech notes that you can cross all the lanes to reach the U-turn decel lane, but then the exhibit shows the merging method.
Okay, so I think this comment is referring to the Minnesota driver's manual. And I think, this will be a bit of a challenge because there are multiple designs of a J-turn intersection. And so you can have these more what we call an extended J-turn, where you would be doing lane merging because that deceleration lane isn't immediately available. So you can't cross all the lanes to get to it. You will have to do that change. I think there tends to be a shift, and I think Vic can speak to this more of if possible to do this more compact design where you have more of these new intersections offering that deceleration lane immediately from the stop, so you cross all of the lanes of traffic to get into that deceleration lane. And again, that's what my research is finding, that's where we see the most errors in that maneuver. Some of them are kind of what we would say are like ticky-tack. It's not really critical, but we certainly want people to know that they should go right into that deceleration lane, because when they don't, if they are making a hard deceleration, or lane change unexpectedly to drivers around them, we certainly could have opportunities for more minor crashes, or again, them missing the U-turn, which isn't ideal. I'll let Vic speak to that as well.
Yeah, thanks, Nicole. The experience to date, and in fact, there was a research report written, I think it was about 2017. I apologize that the name of the report escapes me. But looking at driver behavior at the earlier versions of J-turns, and it was noted that most drivers, even under the extended geometry, are going immediately into that inside lane, right, from the side street. And so that was one of the reasons that the design methodology changed over time to condense those, make them more compact so that drivers can go directly into the left turn lane for the U-turn. So, I mean, from a design standpoint, that's what we prefer. We want drivers to go directly into that left turn lane for the U-turn. It gets those drivers out of the way of the other vehicles, so it kind of eliminates, in a sense, a weaving condition, which we don't want to have at these J-turn locations.
Thank you. Well, we are at time, and I want to thank our presenters today for a really interesting session. As I said, we will be following up with a recording of this webinar and the information that was shared today. And so we will also be sending you information about our upcoming Research Radar webinars, and we hope you will join us at those as well. Thank you, everyone, and this ends our webinar.